This is day 6 of Math 111. Today we're going to do some activities involving attribute blocks. When you come to the classroom, you'll find a kit of attribute blocks on your table. For those at home, I'm going to describe what is in the kit. When you take the top off of the kit, it looks something like this. You'll notice different shapes and colors of the items in the kit. So just looking at what we see here, we see a large rectangle and a small rectangle. We see two sizes of triangles. We see a large square and a small square. We see a large circle and a small circle. We also have a small and large version of the hexagon. Whenever you take things out of the kit, you'll notice that there are 6 of each of these shapes. So I've laid out the large hexagons here, and you can see that there are 2 yellow, 2 red, and 2 blue of the large ones. And then in the picture on the right, I'm trying to show you that there are 2 thicknesses of each one. There's a thick version and a thin version. An attribute is a characteristic that distinguishes one item from another. What are the attributes of the blocks in the kit? What characteristics do you remember seeing? We had different sizes, there were different colors, shape, and then thickness. There are 4 attributes. Again, color, size, shape, and thickness. To completely describe an object in this attribute block kit, you must identify each attribute. For example, the large, thick, yellow triangle distinguishes that piece from all other objects in the kit. So you have to mention each attribute. We're going to be focusing on logic in mathematics today, and the attribute blocks will help us demonstrate some of this. So we have a definition here to start with, the definition of a statement. A statement is a declarative sentence that is either true or false, but not both. So we have some examples down here that help us understand what a statement is. The first example, August has 31 days. This is a statement because it is a declarative statement that is true. The second example, a lion has 6 legs. You may be giggling at this point. A lion does not have 6 legs. But this is a statement in mathematics because it is a declarative sentence that is false. The third example is not a statement. Stand on your head is a command. It is not a declarative sentence. That is the reason it is not a statement. The fourth example is, this sentence is a false statement. This is not a statement because it is neither true nor false. Remember, a statement must be determined to be true or false. We will be using truth tables to demonstrate some of the logic. The truth table shows the possible truth values of a statement. A lot of times we will designate statements with letters such as P and Q, maybe R, S. So on the left here we have a very small truth table. We have the statement P, and P can either be true or false. When we have a pair of statements such as P and Q here, we have to show all possible truth values that the pair can have. The pair can be such that both statements are true, or perhaps P is true and Q is false, P could be false and Q true, or it could be that both statements are false. So you have to have all possible combinations. I would encourage you to notice how this is set up and begin all of your truth tables with your truth values in this order. Notice that for P, the column going down from top to bottom is true, true, false, false. And the column for Q is true, false, true, false. We can combine statements. Compound statements can be made from simpler statements by joining them with words and or. When we use and, such as P and Q, we've formed a conjunction. And here's an example. Let's let statement P be, the floor is dry. Statement Q will be, the kitten is playful. Forming the conjunction P and Q, we have, the floor is dry and the kitten is playful. You are simply joining your statements with the word and. The symbol for conjunction looks like an upside down V. We will be using this symbol when we create our truth tables. So you'll see here in the truth table, I have the columns created for P and Q. And now we want to fill in the truth values for the conjunction P and Q. An and statement is true only when both of its parts are true. So when P and Q both have a truth value of true, P and Q is true. When P is true and Q is false, then P and Q is false. When P is false and Q is true, then the statement P and Q is false. And finally, when both P and Q are false, the compound statement P and Q is false. When we combine two statements with the word or, we have created a disjunction. We have an example here. Statement P is, the girl is walking to school. Statement Q is, the toy is broken. When we combine these with the word or, we have, the girl is walking to school or the toy is broken. The symbol for disjunction looks like a capital V. In mathematics, when we use or, it's a little bit different from when we use or in everyday language. We have an example here. When we say something like, I have enough money to buy a bottle of water or a Diet Coke, we mean that we can buy one or the other, but not both. In mathematical logic, this is referred to as an exclusive or. Think about when someone has told you that you can do one thing or the other. They typically mean that you cannot do both. In mathematics, we allow both parts to be true. So it's either one or the other or both. That's what we mean in mathematics. So again, we see our truth table here, and we've got a new column for an or statement, a disjunction. And an or statement is false only when both of its parts are false. So you'll notice that you've got truth values already filled in here, and the only time this is false is when P is false and Q is false. P or Q is true any other time. We're going to use the attribute blocks to help us demonstrate the and the or. So in this example, select all attribute blocks that are red and small. So think about what was in the attribute block kit. What pieces should have been selected? Only the pieces that are both red and small should have been selected. And since it's really hard in the picture to get some perspective, and there are no large pieces here, you'll have to trust that only the small ones are displayed here. But we have only the small red pieces in the kit. So there are 10 of these. You'll notice that you have 2 small rectangles, 2 small hexagons, 2 small triangles, 2 small circles, and 2 small squares. Here's another example. Select all attribute blocks that are blue and triangular. Think back to the elements in the attribute block kit and think about which ones would be selected now, blue and triangular. What pieces should have been selected? Only the pieces that are both blue and triangular. So you have 2 blue triangles that are large and 2 blue triangles that are small. So there are only 4 pieces in the attribute block kit that satisfy this criteria. Here's another example. Select all attribute blocks that are red or small. Remember what we said about the OR statement in mathematics. You will want all attribute blocks that are red. You will want all attribute blocks that are small. And you want to be sure that you get the small red ones as well. Here we have a picture showing all of the attribute blocks that satisfy the criteria here. So we have all of the red shapes. All the large ones and the small ones are there. And then we need small ones too. So the yellow small ones are included, the blue small ones are included, and then we got the red small ones when we got all of the red, so they are in there as well. We actually have 40 pieces here that satisfy the criteria, red or small. In example 4, we want to select all attribute blocks that are square or thin. Okay, so think about this. It's an OR statement. All right, so when I laid this out, I laid out all of the square pieces first. That was the first criteria. And then we want thin. And again, it's kind of hard to see that we've got a difference here between thick and thin. But you can kind of see that there's a shadow around the thick squares at the top. And all of the shapes underneath the squares are thin pieces. All right, so we have all the squares, we have all of the thins, and this also includes the square thin pieces. There are 36 pieces total in this picture. We'll go back to the logic now. There's another way to combine 2 statements. This is to form a sentence in the style if-then. If P then Q is called a conditional statement. The if part of the conditional statement is called the hypothesis. The then part of the conditional statement is called the conclusion. So we have an example here. Statement P is, the sun is shining. Statement Q is, the grass is green. Our conditional statement, if P then Q, is, if the sun is shining, then the grass is green. So the hypothesis of this statement is the sun is shining. It goes with the if. The conclusion is the part with the then. So the conclusion is the grass is green. The symbol for a conditional statement is an arrow. So you might see something like this, P arrow Q, which is red if P then Q. The arrow points toward the conclusion. So P is the hypothesis, Q is the conclusion. We're filling in the final column of our truth table here. An if-then statement is false only when the hypothesis is true and the conclusion is false. So you'll notice when P is true and Q is true, that if P then Q is true. When P is true and Q is false, then the statement if P then Q is false. So this is the only time we see a false. When P is false and Q is true, our statement if P then Q is true. And if both statements are false, then the statement if P then Q is true. You need to memorize this table. You need to memorize the truth values for and statements, or statements, and these if-then statements. The negation of a statement is the reversing of the truth value of a statement. We do this frequently in English. We have an example here. The car is blue. The negation would be the car is not blue. The symbol for a negation of P is this tilde in front of the P. It is read not P, or the negation of P. So we see in a truth table here that we just reversed the truth values. So when the truth values of P are true, false, the truth values of the negation of P are false, true. Negations are common in mathematics. And some of these conditional statements are very important. They're so important they have names. So we have examples here. We're using the statement P, the food is good, and the statement Q, the cow jumped over the moon. In our regular conditional statement, if P then Q, we would have, if the food is good, then the cow jumped over the moon. When we create the inverse, we're negating both P and Q. So the conditional statement would read like this. If the food is not good, then the cow did not jump over the moon. The converse is formed when the hypothesis and conclusion trade places. So we've got the statement now, if Q then P. It would read like this. If the cow jumped over the moon, then the food is good. And the contrapositive is when we negate both the hypothesis and the conclusion in the converse. So we have the negation of Q implies the negation of P. In our example, it would read like this. If the cow did not jump over the moon, then the food is not good. Make sure you learn how to construct each of these types of statements. We're going to complete a truth table now. Show you how to build one from the beginning. Starting with simple statements, we're going to build columns for the truth table until we can determine the truth value of the whole statement. We want to determine the truth values of this statement. If P and Q, then P or Q. We only have simple statements P and Q, so that's where we will start our truth table. We want to set up the table of the truth values for the basic statements. So you'll notice that I've started with a column for P and a column for Q, and I set it up as I've done on all of these others. The column for P is true, true, false, false, and the column for Q is true, false, true, false. The next thing we're going to do is create columns for parts of the statement and fill in their truth values. So I've got these parts P and Q and also P or Q. I need to know those truth values. So I filled these in. Remember that an AND statement is only true when both of its parts are true. The rest of the time it's false. So for P and Q, you will see the column true, false, false, false. An OR statement is only false when both of its parts are false. So we have for the column P or Q, the truth values true, 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 and false. What we will do now is find the truth values for the conditional statement that we were given. I have all of the parts, and so I can now determine what the truth value is for the if-then statement. When both parts are true of an if-then statement, then the whole statement is true. I see in the second line that the hypothesis is false and the conclusion is true. That gives me a true statement. The third line is just like the second line. The hypothesis is false and the conclusion is true. So I have a true statement. And then finally on that last line, the hypothesis and conclusion are both false. In an if-then statement, this gives me a true statement. So I see truth values true all the way down in the column there. If two statements have the same truth values, then the statements are considered to be logically equivalent. We'll know this because their columns in the table are identical. Right? The symbol that's used for logical equivalence is 3 bars. So an equal sign with an extra bar at the top. An example of its use is shown here. We've got the negation of P and Q is logically equivalent to the negation of P or the negation of Q. You can verify this using a truth table. I would encourage you to do that. Make sure that you memorize the truth values for the AND statement, the OR statement, and the implication.